Hello all, expecting that you'd have watched my previous videos on non-radiative transitions and one of the radiative transition, fluorescence. I move on to brief you on the other radiative transition, phosphorescence. Now we can explain phosphorescence too using Jablonski diagram. Now here we have the Jablonski, the base for the Jablonski diagram, the various energy levels. Now to explain phosphorescence, we need to have one more electronic state, that is the triplet electronic state. I've explained the singlet states and triplet states briefly in the introduction to photochemistry video. Please do watch that for more information regarding that. Now we have the various electronic excited state, singlet excited state, the S1, S2, S3, S0 is the ground state of singlet state. And here we have T1, the triplet excited state, and every electronic state has vibrational energy levels. All these are the basics which we need to know to describe Jablonski diagram. Now let us see the phenomenon of phosphorescence. Now when system is irradiated, it moves on to higher energy levels, as we have seen for fluorescence also. Now from the higher energy level, we know that it will not be stable over there. It has to come down to ground state by losing its energy. And this can be done in various ways. The non-radiative ways of internal conversion, vibrational relaxation and intersystem crossing we have discussed, and also the radiative dissipation of energy via fluorescence also we have discussed. Now here we have the internal conversion, that is from higher singlet excited state to lower singlet excited state. The energy is the molecule system comes down by losing some amount of energy either to the surrounding molecules or in the form of thermal energy. That is called internal conversion. And another non-radiative transition we have explained is the vibrational relaxation. Now here, vibrational relaxation. From here, the vibrational relaxation can also happen if the system moves on from the ground state to the higher vibrational level of first excited state. Okay, and all this internal conversion and vibrational relaxation happens within the same multiplicity. That is, the multiplicity of the system is not changed. Now, but then there is another possibility. That is, when the vibrational levels of the first excited state, singlet excited state and the triplet excited state overlaps, there is a possibility that the system moves on from singlet state to triplet state. Now that is called intersystem crossing. Okay, that is the system goes from the first excited singlet state to the first excited triplet state. Okay, this is also a non-radiative transition, but it involves spin flipping. Earlier, the system was in singlet state, now the system is in triplet state, where the electrons are unpaired or the electrons are in the same spin, parallel spin. In the singlet state, the electrons will be in the anti-parallel spin, while in the triplet state, the electrons will be in parallel spin. Okay, and hence, because of this spin flipping is necessary, intersystem crossing is a bit slower process. We have discussed this in the non-radiative relaxation video. Now, from the higher vibrational level of the triplet state, the system will come down to the lowest vibrational level of the triplet state. Okay, via vibrational relaxation again. because this dissipation of energy is within the same electronic state. That's it. That is why it is the vibrational relaxation. Now, from the lowest vibrational energy level of the triplet state, the system will move down to the ground state. So here also it is not, it is not stable because it is at a higher energy level. Now, when the system comes down to the, or jumps down to the ground state from the first excited triplet state, as in the fluorescence, this also emits radiation, loses energy in the form of radiation, and that is called phosphorescence. So phosphorescence involves transition of system from first triplet excited state to the singlet ground state. Okay, so while jumping down to the ground state from the triplet state, again there will be a spin flipping. That is, the electrons which were having parallel spin will come by the time it reaches the singlet ground state, the spin would have become anti-parallel. Okay, so spin flipping happens. So for phosphorescence to happen, the spin flipping happens twice. So one over here at the intersystem crossing stage, and one over here while emitting radiation in the form of phosphorescence, the final energy dissipation. And because of all this, there are too many steps to be crossed. The phosphorescence is a bit delayed. It's a slow process. Alright. Another way is for phosphorescence is the system from the lowest vibrational level of the triplet state will come down to higher vibrational levels of the singlet ground state. That is also possible. And then by emitting radiation, from there, since it is still in the higher energy level, it comes down to ground state by vibrational relaxation. Okay, so these two situations, or it can to any vibrational levels, from T1 to any vibrational level of singlet ground state, when there is movement of or jump of the system from T1 to any of the vibrational levels of the ground state, it results in an emission of radiation, and that is called phosphorescence. Okay, now we need to know, we need to focus on few more points regarding phosphorescence. Now, this phosphorescence, as we said, it is the movement of electrons or system from triplet excited state to singlet ground state. And because of that, the energy of phosphorescence is less than the energy of incident or excitation or irradiation. Okay, but the opposite will be with respect to wavelength, because E and energy and wavelength are inversely proportional. Okay, and as in the case of fluorescence, since the system from T1 can move down to any of the vibrational levels of S0, we can have phosphorescence radiation over a range of wavelength. Alright, and so since there are a lot of pathways to be crossed, this is a slow process, and one of the reasons is the necessity of change in spin multiplicity. And this another very important factor regarding phosphorescence is that the luminescence is delayed by more than 10⁻⁻⁷ seconds after excitation. Okay, so that's why it's a slow process. So because of the change in spin multiplicity required, the luminescence is delayed by more than, usually it is considered to be 10 to the power of minus 4, 10 to the power of minus 1 second. So it is so slow. And also, this continues to remain there, that is, phosphorescence phenomenon continues for some time, even after the removal of the source of excitation. That's important. That is, the material will be luminous even if you remove the source of light. Okay. Now, you would have seen the self-glow toys, glow-in-the-dark toys, stickers, paints, etc., which glows in the dark. Okay, so that is because of the phosphorescence phenomenon. Okay, we use dyes containing having phosphorescence materials. Okay, now let us see the pathway by which phosphorescence can occur. Firstly, absorption of light occurs, and then followed by internal conversion, followed by vibrational relaxation, then inter-system crossing, then again vibrational relaxation, and then phosphorescence. Okay, absorbance, internal conversion, vibrational relaxation, intersystem crossing, vibrational relaxation, and phosphorescence. This is the pathway. So it's a bit long pathway, and that's why this is delayed process, and also it takes some time. Okay, when you compare it with other non-radiative relaxation phenomenon and fluorescence. Now, a few examples of materials which exhibit phosphorescence. Inorganic phosphochemicals, compounds like oxides, nitrides, silicates, sulfides, halides or oxyhalides of alkali and alkaline earth metals. Okay, particularly, but these must be doped with some amount of activators ions which are of rare earth metals. Okay, so alkali and alkaline earth metal sulfides having some amount of heavy metal ions can act as phosphorescent material like zinc sulfide, calcium sulfide, then strontium aluminate. Also, some certain complex organic compounds also exhibit phosphorescence, and these are used in OLEDs, that is organic light emitting diodes. Okay, so these are few examples of phosphorescent materials. Okay, alkali and alkaline earth metal sulfides doped with transition metal sulfides, certain complex organic compounds which are used in OLEDs. And all these phosphorescent materials find use as in the stickers, glow-in-the-dark stickers, glow-in-the-dark toys, paints, wristwatch dials, clock dials, etc. And just for your information, the discovery of radioactivity was initiated or was started during the study of phosphorescent materials. So we can say phosphorescence was the precursor for the discovery of radioactivity. Alright, so these are the informations which I wanted to convey to you regarding phosphorescence. If you have any more clarifications, please feel free to ask them. Right? Thank you for watching this video. Thank you.